we go. And we'll share the screen. Okay, I think we're in business. The only question is how long I can stay in business. I have a new headset. Hopefully the microphone is a little bit clearer than before. Ironically, oh, we got one more person waiting here. Ironically, this is the headset they gave us when they took away all of our landlines in our offices and made us switch to Skype business for first calls. I've worked at Iowa now almost a year and a half, and no one has ever called me on my landline. The only calls I got are spam and people trying to find someone who had the number 10 years ago. So, but the headset is now coming in handy, so I don't have to worry about running out of juice. All right. And away we go. Hide self view. There we go. Now I can see you guys. I would love to have as many cameras on as I can, but I understand that takes a lot of bandwidth, and also you may be in your pajamas or whatever. If you don't want to be on camera, that's fine. But I enjoy seeing your happy faces. Let's talk about formative assessment number 5, the second to last one. I've decided to try and take notes as we go over this. That way, in case the audio gets garbled or otherwise we go off the rails, we can get back. So this will be, try and do this as interactively as possible per our usual, but we'll see how it goes. So question 1, when models predicting outcomes separately are a possibility, what are some advantages of predicting multiple outcomes simultaneously? So what did you guys have to say about that? You can chat, you can unmute yourself, you can do whatever you'd like to be able to help me out here. What did you guys have to say about that one? What are some situations or research questions in which it would be helpful to predict multiple outcomes simultaneously? Kelly says multiple intercepts is helpful, advantageous when we want direct interpretations rather than indirect. That is true. However, that is not what I'm currently asking. That is more questions 2 and 3. So Jeff says we do not need to run several models for each outcome. We can run one model instead. Yes, that is a good reason. Uh, each outcome has its own linear model, which allows you to do comparisons across the models. Yeah, there we go. Comparisons. Molly says you can examine differences in predictor effects across outcomes, and then you don't have to control for time one and repeated measures designs. Ah, yeah, that's also true. Two separate ideas though. So the idea of comparisons across the linear models estimated simultaneously. That allows you to ask whether or not a given predictor has a stronger effect on one outcome than another. That's helpful in situations in which you have more than one measure of a given construct, and so you can see whether or not there's differential sensitivity to the measures to whatever predictors or manipulations you're asking questions about. That can also be hacked to examine differences between the measures as an outcome, so predicting difference scores. That's the example that I have for you today. You don't have to control for time one and repeated measures designs. So yeah, is that something that you guys have seen before or been advised to do by chance? No, no, maybe? Yeah, just yes. So the problems with that approach, um, if you have, say, a pre-test and a post-test, a very common analytic strategy is to use the pre-test score as a predictor of the post-test. And so then you're supposedly just examining change. That's not actually what you're doing. What that model gives you is something called residualized change. How much there is change in an absolute sense is removed from the model because you're predicting the post-test from the pre-test for each person. And so that's going to capture any absolute change. And all that's left is relative differences relative to that prediction. So it's not predicting a difference or a change, it's predicting residualized change. It is problematic in experimental designs in which groups that you are trying to make some sort of causal inference about, say, a treatment versus a control, if the groups are not equivalent on the pretest, then the answer that you get back will be incorrect. So I would encourage you not to do those models and instead to do a multivariate model in which you predict the pretest and the post-test directly. And the example that I have today is not a pretest post-test, but it's the same idea where what was interest is the difference between them, the change. And so predicting both allows you to say, what are the effects of my treatment or other covariates on the pretest? What are the effects on the post-test? And how do my predictors predict change? One model can give you all three pieces of information simultaneously in that case. So those are all good reasons to do a multivariate model. I think Jeff had a comment about we can run one model. If you do find that a predictor's effect is equivalent across outcomes, you can specify one slope rather than multiple slopes, and that one slope in theory should have higher power. Particularly if there's missing data involved, then you can sort of borrow information across outcomes. So multivariate models are advantageous in that circumstance too, even if you don't have a hypothesis about differences in the effect of predictors, to the extent that you can estimate fewer slopes and predict more things. That's a good thing. Got good strategy to pursue. Very good. I think after this is done, I'm going to save this chat and use this to try and fill this out rather than typing in front of you. Is that okay with you guys? Yeah, okay. Because otherwise you'll just sit and watch me type, and there are fewer things more boring than that, like watching paint dry. Okay, so number 2 then. Well, first, before we move on, any thoughts or questions about number 1? Good? Okay. Then now, how do we set this up? Setting up multivariate models and knowing exactly what the results mean can be very tricky. So that's why I wanted to really drill in on those and give you more chances to practice with that. Describe in general terms how the parameterization of the fixed effects changes in multivariate models when a general intercept is used as to when outcome-specific intercepts are used instead. So who wants to tackle that? I'm watching the chat window eagerly to see what wisdom you have for me. Dun, dun, dun. So Kelly had a thought on this. Multiple intercepts is helpful when we want to have direct interpretations rather than in reference to. That is true. So in which parameterization is that? Did she say? I'm trying to remember. Multiple intercepts, yes. So outcome-specific intercepts. So if I have a separate intercept for each outcome, then each other fixed effect is also outcome specific if I set it up that way. So I have the effect of the predictor on outcome A, I have the effect of the predictor on outcome B. And each is a separate linear model without being in reference to each other. Kelly says again, with outcome-specific intercepts, there is a turning on switch parameter for each intercept, each beta. The model equation has more variables than the general intercept model. Not necessarily more variables. It should actually work out to be the same. The models can be made equivalent. It's the question of what the main effects of each DV mean. So this may be where having a more concrete example would help. So let's say that we have our stacked data set. We have, let's go 2 outcomes just for today. And we're going to see this, by the way, in the example. So this is just a real quick one here. So we have y equals, and if I have outcome-specific intercepts, then I might have, I'll have dVA and dVB, and then I have dVA times my predictor and dVB times my predictor as well, something like that. And then the all-important no int to shut off the general intercept. In this parameterization, the main effects of dV are intercepts. They are not differences. Here, this is the effect of the predictor for that outcome. This is a separate parameter for the effect of the same predictor for a different outcome. So this is what I think Terry had said earlier. We have separate linear models going on simultaneously. If you compare that to a general intercept parameterization, where I'm going to add the implicit intercept here. In that case, one of the dummy codes is redundant, so we get that out of the way. We would switch to a main effect, and it would look like this. So there's not more parameters. These models are equivalent. There's 4 fixed effects. The difference is in what they mean. So dVB here, that is not the intercept for the second outcome. It is the difference in the intercept between outcomes. Because dVB is relative to this column of ones that applies to everybody. So like if I have a data set here, the intercept column, and then the dVB column. Hang on. 1, 1, 1, 1. If I had, let me make another one here, dVA, dVB. Let's say that the first 2 rows are for, this one is for an A person. This one is for a B person, or B outcome rather, excuse me. Yeah. Okay. Yeah, we only need 2 rows to make this work. So the first parameterization lends itself then to these 2 right here. dVA is functionally a column of ones only when it's the A variable, and dVB is a column of ones only when it's the B variable. Versus in the second parameterization with just these 2, we've got the intercept is for everybody. So then dVB is a difference. It represents a difference, just like an effective group would be in any other type of traditional predictor analysis where you have a reference group and then you have a contrast for how different another group is relative to the reference. It's the same idea here. We have a reference dV, and then we have how different dVB is from the reference one. So this first parameterization with outcome-specific intercepts, that gives you what the intercept is for each outcome, what the predictor effect is for each outcome. If you want the differences between them, for instance, the difference between the intercepts, it would be the slope for dV A and B, or excuse me, these 2 demicodes, the difference would give you the difference in their intercepts. If you wanted the predictor slope difference, that would be dVB times predictor minus dVA times predictor. So the differences then are linear combinations. This route gives you the differences directly. dVB is how the B intercept differs from the A intercept. dVB times predictor is how the slope for the predictor differs for B relative to A. If you want to get whatever it is for B These two together would give you the b's intercept, and these two together would give you the b's slope. Okay, how are we doing? Okay, 2 thumbs up. Black box people, can I get a thumbs up or a thumbs down? Watching, watching. Oh, there's one. There's one. We got a couple. Okay, they're slowly coming in. So like I said, we have an example today that's going to do much more of this, but just in terms of general strategy, um, it's like what are you interested in? Are you interested in differences between outcomes as a thing? If that is the case, then using a general intercept, this version of it is going to more directly align with what you want to know. If you're interested in what is the linear model predicting each outcome, not differences per se, but just what is the predictor's effect for each, the first parameterization is going to be more directly give you what you want to know. But if you put in all of the fixed effects, they should be equivalent. All right. Okay, what's the next one here? Describe what happens when including a categorical predictor for which outcome is which. What does the program then do behind the scenes? So this is when you take your, say, DV in this case, and rather than coding it up to say this is a dummy code for A and this is for B, you just tell it that DV is categorical, meaning you put it on the class statement in Stata, or you make it an I dot factor variable, or class statement in SAS, excuse me, or I dot factor variable in Stata. So what is it doing for you when you do that? Eagerly watching my chat window to see the responses come in. There's one. There's two. All right. Jing says the program does internally using class and SAS to create the dummy-coded variables. The dummy-coded variables create contrast to differentiate the categorical variables, and the program will determine how many contrasts to use. Yes, indeed. It does your dummy coding for you. It makes one dummy code for each unique category of the predictor declared categorical. Terry says it creates dummy codes for each outcome behind the scenes. Yep, same thing. When you include a general intercept, it leaves out one column. Yes. And so which column is left out, then you have to figure out in the software. It's the last column in Stata. Nope, screwing it up again. It is the last column in SPSS and SAS. It is the first column in Stata. And so then the other dummy codes represent differences relative to that missing column as the reference. And yes, Stata I dot prefix that's how we specify it, and in SAS it's on the class. So yes, it's creating the same dummy codes, but it's doing so internally. And that's why every time you reference DV in the code, so if I had something like this in this example here, I'll do a third one. We say y equals dv, and dv is categorical. Then everywhere else, like if I had an estimate statement, estimate me something, you had dv, you'd have two values after it because you'd have to turn on or off the ones and zeros that correspond to those internal created dummy codes. So like if I had an A and a B, and I had this dv right here, if I put a 1 there, that means whatever I'm talking about, make it for dva. Don't use dvb. If I did something like this, a -1 and a 1, that would give me the difference between the two. So it has to know what to fill in for each of those internally coded variables, including the one that it left out. The one that it left out either being first or last based on your package. Incidentally, we're going to be moving to M+ software and Stata to do path models. That's starting probably next week. There is no convention for this in M+. It doesn't do class variables like this. You only have to do your own dummy coding. So that skill will be important. Whether or not Stata can use class variables depends on which version I learned. It doesn't seem to be able to do it in some of the earlier versions, but it has in later versions. So because it wasn't consistent, I don't use it in any of my examples. I just use my own dummy codes because I know for a fact that that works, and it looks more like the rest of the codes for M plus that I'll show you as well. All right. I think we got most of that covered. Other questions or thoughts? Jeff says no. All right. Well, let me ask you something really important while the internet is unstable. Did anyone watch the last Grey's Anatomy from last Thursday? No, not. Yes, Lexi. Was that not like that was such an awesome episode? It was. It really was. I don't want to give any spoilers out there, but it was just one of those like classic Greys. I really wanted them to see like to do like a COVID like thing, right? I want to see all of them with like, using garbage bags as protective wear and all the chaos. I wanted to see that, but apparently we're not going to do that because it's a TV show and we don't want people to get hurt. So yeah, I'm not. That's not. Yeah, yeah. There'll be like a pandemic, and everyone will be like, "I don't want to hear about a pandemic." Yes, it is a very good show. I don't think it's dropped off much. Like, some shows sort of like start to die and it's like in season 16 and you'd think, it would have jumped the shark by now, but no, it's still really good. Yeah. Wow. Arteries as vein or as Twizzlers. That's going above and beyond. That's a no for me. I don't want to pretend I'm eating internal body parts. Um, you did, but yes. And yes, there's commentary in the comments here. Yes, Ellen Pompeo is very uh, politically involved, and I also like the fact that she's like, what, 55 or something in real life, and like she's still on the show considered to be like a hottie. Like everyone always makes a big deal out about how she's like super accomplished and she's a hottie, and I'm like, yes, middle-aged women can be hotties. So goals, hashtag goals. But not during a pandemic. It's kind of hard to be a hottie when you live in pajamas and you can't leave your house and your son won't leave you alone and, all that stuff. But anyway, are we still not frozen? We're still not frozen? We're good? Okay. Then let's hop into example 5A. So this one is starting off with still just general linear models, which is why we're starting here. And then the last part of it is going to treat it as ordinal. And so then we'll have to jump into lecture 5 to be able to do that. So can you all see this handout? Okay, this is an example that I've been doing for years, but I super tricked it out for this class, so you guys should be happy with me for this long, very extended example. How many pages is this? 24 pages. Not quite a personal best, but it's closing in on one for one set of handouts. So these are real data, which is why they are not in, thank you. It is impressive, right? I have a 24-page handout out of what accounts to be 4 means. I kid you not. 4 means, 24 pages. Boon. So these are real data. The backstory is that the reason this example exists is because of reviewer 3. Okay. Now, for those of you who haven't experienced this, reviewer 3 is the meme for the reviewer who makes it impossible for you to publish your paper. They think that you should cite them. They think that they know everything about statistics, and they say asinine things, and you have to respond to them because they're a reviewer. Nowadays, it's been reviewer 2 is this person because it's hard to get 3 reviewers for one paper, and so reviewer 2 is the new meme. But yes, if you're bored, there is a video on the internet that I am not going to send you because it is very inappropriate, but it's all about Reviewer 3. So you should search for that. It's funny in a dark sort of way. But anyway, these data were from a colleague of mine at the University of Nebraska. She's Sarah Gervais. She's a social psychologist there at Nebraska. And she was addressing a picky reviewer comment that she had analyzed a different score, and the reviewer was not happy about that. And so she wanted to get advice on how to address this person's criticism. So, what the different score was about was for this picture right here. I found this on the internet. This is called a figure rating scale. And there are two answers that you're supposed to provide. Well, actually, there's more than that, but there's two they were interested in. And so there's separate little figures for men and for women. One question was, which of these figures looks like you? So it's like your actual rating, and you give a number as to which one best looks like you. And then the second one is, which is the most ideal body? What should you look like? Spoiler alert, women think they're too fat. Okay, that's my 24-page handout in one sentence. Okay, that's what we're going to find. And so this was something that she wanted to report just as an aside, and she had to address this comment. And so I was like, well, the reviewer sort of has a point. Like, different scores can be problematic in that all you're looking at is the difference, and you don't know whether what caused the difference, right? Like, is it a gender difference in the actual, or a gender difference in the ideal, or a difference in the difference? So we're going to look at all three of those things in a multivariate model. And use this as an example of how to set these things up and to make sure that we know what the model is telling us based on how we set it up. So the punchline to this is that she was able to successfully defend herself against reviewer 3. The paper got published, and I asked her if I could use her data for a class example, and she said sure, and so that's what we have. So it ends on a happy note. So what we're going to look at then, these are college students, 78 men and 67 women who completed this measure and provided ratings of what their actual body was and their ideal body. And what we're interested in is this concept of a discrepancy, sort of how unhappy you are relative to what your ideal should be. That's the concept that they're interested in. It is a difference. That's what they want to know, and whether there are gender differences in this body discrepancy. So we're going to do this two different ways. First as a multivariate model in part one of this handout, and then in part two as a series of path models to examine the same thing. So here's what, make this a little bigger. This data set here provides a description of what it looked like initially, where this is a traditional wide data set, one row per person. And we have a code that's numeric for what their gender is, just a 0 or 1. I also have a labeled version of that column. The reason we need both, we'll see in just a little bit. It's not actually redundant. I have a rating for actual body, an ideal body, and then a difference score, computed as such. So to be able to predict the actual, the ideal, and or the difference simultaneously, we need to stack them into a single data set. Single column rather. So what I did is stack all three outcomes. Even though one of them is going to be redundant, any one model can only predict two at the same time. I wanted to show you different permutations of what this would look like. And so I have all three outcomes. So each person in the stacked data set has 3 rows. I had created, as you'll see, I'm going to use their actual and their ideal as predictors of their difference. And so I centered those at 4 in doing the stacking process. And then here are my 3 dummy codes, DVA, DVI, and DVD. So A for actual, I for ideal, and D for the difference between the two. And then here's the actual rating. So just for instance, the first 2 people in this data set are men. They both think that they're kind of skinny. They rated themselves as 1s and 2. They agree that they should be a 3, and so then there's the difference. So both of these men want to be heavier than they actually are. That's what a positive difference means in this context. Okay, good so far on the story? All right, now how did I do this? Well, state a code first. Imported the original wide version of the data. I created two new variables that are centered versions of actual and ideal to be used as predictors later. Here's another instance of having to rename. So in order for Stata to be willing to stack those three outcomes into one column, I had to rename them so that they had numeric suffixes. So they were originally called actual, ideal, and difference. I renamed them to be rating 1, 2, and 3 so that I could stack them. I also renamed the gender variable with the right capitalization. So this is one of the things that drives me nuts about Stata is Stata only allows lowercase for all of its commands. And when SAS exports data in a Stata format, it automatically translates all the variable names to lowercase. Um, I don't like that because I use this title case to help me understand what the variables mean. So it's like M versus W is what this variable means, not which is what it looks like when it's all lowercase. Yes, that was I'll have to see what the YouTube auto translators make of that one. That's what this word says to me versus this. So I had to change it back just for my own sanity. Then under the reshape, rating is going to be the new column, person ID. So this is again another one. I didn't bother to change it. I'd only changed one, but this bothers me too. Personid is what that says to me. Personid. No, it's person ID. It's going to use that to figure out how to link the rows together. DV is a new column that it's creating, and that's going to have the numeric suffix 1, 2, 3 that were created here, and so I added a label to it. That way it will actually have information about what 1, 2, and 3 mean. And then here's the three dummy codes, DVA, I, and D, set to 1 for each of the variables, and labels. SAS did all of that in one shot. So anything you want to be done to the long data set, you do ahead of the stacking code. So I created the new predictor variables first. Then here's my 3 lines of code that create 3 new rows for each person. Any variable that is not mentioned here is kept automatically, but I'm making a new column that's going to be DV, another new column, DVA, I, and D, and another 5th new column for rating, and then systematically putting in the information for each variable, and then dropping the old outcomes after labeling. So you've seen a couple examples of these so far, but are there any questions on how to stack data? You'll get a chance to practice this in your next homework as well. Pancakes and crepes. Okay, any other questions on the data setup broadly construed? Nope. Okay. Then away we go. First thing here, I just wanted to give you a sense of how these things shake out by gender. So these are frequency tables. The first table right here, see if I can highlight that. Yep. That is a cross tabulation of the number of people who rated themselves in each category of 1 to 9 for what they actually are by gender. It looks like there are, just eyeballing this, it looks like the men are a little bit more stacked on the lower end. The women are a little more variable. Here's the ideal. So note that actual goes from 1 to 9. They used the entire response scale, meaning some people thought that they were super skinny and some people thought that they were larger. Ideal, though, is ranging from 2 to 6 only. So everybody thought that their ideal would be somewhere between, yeah, the 2-person and the 6-person. And then here's the difference. Here's where the story is going to be. A negative difference means that they think their ideal is smaller than what they think they actually are. And you see more women on that side of things than men. A positive difference means that they think they should be heavier than what they actually are. And that is much more common in men than women. And then here's the middle category, the number of people who think they're fine just the way they are, definitely in the minority relative to this. So in describing these numbers, are these really numbers? Because these aren't like weights or body mass indices or inches or pounds or anything, right? Are these numbers? Lexi says no, question mark. They're categories, aren't they? Yeah. How would you describe this measurement scale? Ordinal-ish? Yes, exactly. Sort of. It is ordinal. Um, Ironically, reviewer 3 did not bat an eye at that. They were angry that it was a difference. So, given that it is ordinal, um, take what follows with a grain of salt. I will show you how to treat it as ordinal, but there are some additional complications in doing that in terms of the analysis. So for now, we're treating it as interval. What kind of distribution it should have is what I looked at next. So what I did was run the same model for each outcome separately, the actual score, the ideal score, and their difference, just predicted from gender, because that's what the final model is going to look like. And normal-ish for the residuals. I mean, it's not as terrible as you would think. So based on that, there's only one distribution that looks like it might have a little bit of over dispersion, but not that the others are pretty much okay. So I would say even though this is a little questionable, it's arguably reasonable to treat these things as with a regular general linear model, something where we're saying that the measurement is interval, the residuals are normal, and so we can look at the differences between men and women as numbers and have that make sense. Arguably reasonable, I would say. Oh, you guys are frozen again. Am I frozen? No, you're back. Okay. It's like you freeze briefly and then it comes back. Either that or you're really, really still. Yeah. The black box people are incredibly still. If I wanted to be one of those professors, I could turn on the attention thing and it would let me know if you minimize my window for more than like 30 seconds. There's a setting on Zoom to do that. I have not done that yet, but I could. I could totally spy on you. Yeah. Well, for that reason, I have heard of other instructors who require the cameras to be on so that you can see if you're actually paying attention. And the internet, of course, has already solved that problem. I saw a thing about someone who made a video of themselves sitting there so that they could play it during boring conference calls and actually be away from the computer. What if you have two windows up? I think if it's not in focus, I think that's when it dings it. But yeah, this person made a video of him just sitting there in front of his camera and it loops. So even so, the only way he could get called was if he got called on, I think. And so I tend not to do that. But anywho, we're unfrozen again. All right. So I'm going to show you a whole bunch of permutations of how to do this. And that way, the next time that reviewer 3 tells you, you can't predict a different score, it's not okay, you will have an answer. Actually, yes, it's a linear combination of if I predicted the original outcomes, and it's fine. You appreciate not having to do video. So much Zoom all day. That's okay. Yeah, I like seeing you guys, but I also want to be respectful of your privacy. Um, that's what the virtual backgrounds are fun, but not everybody's system, mine included, is capable of that. So as long as you're here and making The effort to be here, I'm happy with that. And hell, we have more people in this class than have black boxes in front of me. I hope they're making the effort to watch the videos later, but I understand that life sucks right now. And best effort sometimes is just like getting out of bed. So being here at all, great. Being here on camera, even better. I miss your guys' faces, and I really hope that this is not the fall semester. But that's maybe what we're looking at. So, anywho, we're looking at an example. That's what we're looking at. I'm looking at it sideways here. So, Model 1A, that's what we're looking at. What I'm going to do is predict actual ratings and ideal ratings simultaneously. Molly says, I will cry if we have to do this for the fall. Yes. Yes. It will be a problem on a global scale if we have to do this for the fall, because everyone who is paying like international tuition or out of state tuition to come to Iowa would be like, why am I paying so much money to sit on Zoom? I could Zoom for like 20 bucks a credit hour at my local, whatever university. So, at least at the undergraduates, that's probably true. Students are suing their schools. I would not be surprised. Um, it's hard to argue that anything could have changed, right? In hindsight, at the university level, we did what we were supposed to, which is be responsible, and it sucks, but we also can't just like not we can't shut down. So, anywho, we're gonna get through this. We are. All of the higher ed finance people are freaking out. Yes, yes. I'm I know I've been watching all of the various, cheerleader emails that our university has been sending us, rah rah. Oh, by the way, here's a Zoom session on how to improve your mental health. Do you know what would improve my mental health? No more freaking Zoom sessions. That's what would improve my mental health. I was like, seriously? So, um, anywho, I lost my train of thought. I'm just rambling at this point. Oh, I know what I was going to say. All of that communication was that we're getting paid through the end of the spring. So there's that. And I'm like, well, what happens in the summer? So I don't know what happens in the summer. No one has said. So that's those are the things that I've been thinking about, in addition to predicting different scores and all of the drama with that. So yeah, let me do my job. How about that? I'll do my job instead of rambling. So we're using mixed in Stata. We are shutting off the general intercept in this version of the model. So you're going to see all different permutations here. In this version, we are predicting actual ratings from gender. We are predicting ideal ratings from gender. That's what's going in the model. So we have DVA, DVI. Those are going to be my two intercepts. We have our friend the hashtag making an interaction term. So men versus women in predicting DVA, men versus women in predicting DVI, and something new that I learned here. I had to learn this to build this example. That if statement. Have you guys seen that before, Stata folks? Yeah, it's a filter. What it does is only run the model on people who meet this condition, and it's if DVD equals 0. What the equal means is a conditional. How do I say this? It meets a condition. So if this is true, it's not assigning a new variable. It's not changing anything. Very useful. Yes, it is. So the reason that I had to stick this in here is because let me go back up to what the data set actually looks like at this point. There we go. Saw it drive by. The data set looks like this right now. I have a row for actual, I have a row for ideal, and I have a row for their difference. For this analysis, I do not want the row for the difference in the model. That will mess up the coding as to what each of my DV-specific intercepts means. So I am telling it, do not run the model on the row that has the difference. Okay, scrolling. There we go. This is the same as before. I am fitting an unstructured R matrix. Do you remember what unstructured means? See, I'll keep asking questions to see if I can catch anyone on the loop who's just sitting in front of their computer. Because loops can't answer questions. Gets to be what it wants, yes. So unstructured R matrix means in this context that the residual variance for the actual ratings is one number. The residual variance for the ideal ratings gets to be another number. There's no constraint that they're the same, and the covariance between them is estimated. That is not a default in software. So that is something to pay attention to make sure that you've specified that. For two outcomes, there's only one covariance, and so that's not that many parameters. I'm not going to worry about trying to simplify things. I'm using Satterthwaite degrees of freedom. So it's going to use the number of persons as the degrees of freedom whenever you have an unstructured matrix. The matrices themselves get printed here. And here is all of the things that I would want to know. You need to make some flashcards for this. Yes, then you could hold it up to your camera, what unstructured means. So you're going to see this same configuration of all the things you would want to know from this model in every example, but how they get made is what's going to be different. So what the ingredients are that go into making each of these. So line by line here, the first 4 lines are what the model says the mean should be for each outcome for each person. So because these are predicted means, outcomes, we have the intercepts in here. I've included everything that would be relevant in making each of these. So because this is for actual, the first intercept for DVA is on. The intercept for ideal is off, coded 0. Likewise, because this is for men, the interaction term is coded 0 because men are the 0. And this one is 0 because it would be for the ideal outcome anyway. For actual women, we need the intercept for actual plus this term right here for how the intercept differs of women relative to men as the reference group. For ideal women, we pick up the 1 for the intercept for ideal and the 1 for this interaction term, turning it to 1. So the model is somewhat asymmetric in that these two are intercepts. These two are intercept differences for each outcome between women and men. Okay, does that make sense how this is set up? Okay, black box people. There's 1, 2, 3, got it. Okay, I want to see a field of yellow thumbs. I'm missing a couple of you. No, okay, got most of them. All right, then we get to simple differences. So one thing that we might want to know is how do men and women differ in each of these questions to begin with? Is it that women think they're heavier than men on average? Is it that women's ideal is different than what men's ideal is? So that's the simple effective gender for actual is right here, or not simple, excuse me, just the effective gender in this case. And the effective gender for ideal is right here. So those are directly given by the model. The last 3, these are linear combinations. So A versus I is my way of saying actual versus ideal. So this is the idea of this body discrepancy, how different you are relative to how your ideal is. So to get that, let's do this one first. It's the difference in the intercepts if it's for men. So the intercept for ideal minus the intercept for actual gives me their difference. Because it's for men, the interaction terms stay at 0. If I want it for women, then this part gives me the difference for men. To add to it, to get to the difference for women, the coefficients take on whatever pattern they were assigned for the dv's. So because dva is -1 here, this is -1 here, because women would be a 1. 1 times this -1 gives us that -1. Because dvi had a 1, times 1 for the women is 1 here. So this tells us how discrepant these bodies are for each type of gender. And then last but not least is the one thing that we cared about to start this whole story. Is there a difference between men and women in how discrepant they think their bodies are? It's a difference in the difference, otherwise known as an interaction term. And here is the same thing in SAS. The analog to this if DVD equals 0 in Stata is right here in SAS. It's a where statement. Where means the same thing as if. And it's only one equal sign because SAS does not differentiate between single and double equals. We have no int to shut off the general intercept in SAS, which is the analog to no constant up here. And then the lincoms and estimate statements are the same in structure. The only difference, of course, is the absence of plus signs and multiplication signs, as well as the star instead of the hashtag for those. Okay. How are we doing? Yellow thumbs. Okay, lots of yellow thumbs. Real thumbs. Okay. Let's see what happened. Just as a reminder, in using mixed, to report -2 log likelihood to 2 decimal places, you have to pull it from this table, the iteration history, because in the model fit section, it doesn't provide it to enough precision. Here is my R matrix. Okay, what is that? We'll do a little review. Kelly says. Okay, Kelly's dog says. What am I looking at here? There's a lot of numbers on this page. I want to make sure you guys know what you're staring at. This would be SStat W covariance comma correlation if you're looking at the data output that goes with this example. Way says it's a covariance matrix. Yes, it is. It is the residual covariance matrix. So column 1, row 1, that's whichever DV is first according to the variable, this DV variable. That goes in the repeated in SAS, and it goes in this right here in this unstructured little thing in Stata. So because A is first on that variable, that means that 3.57, that is the variance unexplained by gender in the actual ratings. The other variance then is the variance unexplained by gender in the ideal ratings, and note that it's a lot smaller. So using unstructured is advantageous in this case. I'm not even going to do a significance test for this. I'm just going to eyeball it and say, yeah, that's a lot smaller. Other structures such as compound symmetry would say that both of those numbers have to be the same value. They would constrain them to be the same, and we don't want that. That would not fit well in this case. This number right here, that is the covariance. So covariance definition is how far above the mean you are on X, above the mean on Y. So this is the mean that's predicted for you based on your gender, but it shows a positive association between the two. Covariance is in units of the original variables, which makes it hard to explain. And there's the correlation instead. So if you standardize actual and standardize ideal, after doing that standardization, the ratings tend to agree quite a bit. So people who think they're heavier think the ideal is heavier as well, relatively speaking. That same information is down here as well. So what's in the R matrix, this is where it gives you the standard errors. Here is the fit statistics again, and note that I added this 4 here, just to remind you that it only gives you one digit of precision. And here are the estimates. So I have these things labeled for you, Proclisa, of course, but each of these is an intercept, and it worked out they are literally the same number. So given my coding scheme, DVA is the intercept for the actual outcome when all of its predictors are 0, which is for men. So men on average rated themselves a 4.18 for their actual rating. Men on average rated the ideal the same. So on average, men think they're perfect. Come on, that's worth a laugh. Jeff's like, no, I'm not having it. On average, men think they're perfect. There's no difference between the actual and the ideal. So we can interpret these effects of gender a couple different ways. Let's go this way. So this is going to give us the gender difference in the actual ratings. So the group coded one is the women. So women think they're actually about a half of a whatever the hell this is bigger, which is not significant. So there's no significant gender difference in what people actually think they are. Ideal, though, there is a significant gender difference. Women think that the ideal body is smaller than what men think the ideal body is. Now, these set of 4 numbers right here give us the ingredients to answer the primary research question, but they don't give it to us directly. So the primary research question again was, is there a gender difference in discrepancy? Right? Discrepancy as the difference between actual and ideal. We don't have that yet. It's a linear combination, though, of what we do have. So here's the 4 means. Remember I told you a 24-page handout based on 4 means. Here they are. These are the 2 gender differences that we already had. And here's the stuff that goes into the research question. So the difference for men between actual and ideal is the difference between these 2 numbers right here, which is 0 to like 14 decimal places. So there is no difference for men between what they actually think they are and what they ideally want to be on average. But women, let me get the right numbers here. Actual women and ideal women. On average, women want to be about 0.8 units smaller. And because men don't want to be any smaller, that translates into the same number actually for the interaction term. So that number right there, that's what we wanted to know. That is the gender difference in body discrepancy. Women want to be more smaller than men want to be, on average. And that is significant, as you might expect, based on just these means and the standard errors. So this, by the way, is the kind of thing that I'm going to ask you to do on your next homework. You have two outcomes and two groups. So you have the outcomes are performance in making pancakes and in making crepes, and the groups are people who were trained to make better pancakes or they were trained to make better crepes. That's the story. So this is the type of setup then that I want you to be able to practice getting all of the comparisons out that would be relevant. Okay, how are we doing? My homework will make me hungry. Yes, it will. Crepes are hard to make. That's sort of going to be the punchline in the story. Crepes are much harder to make than pancakes. You have to have special equipment even. Um, so one last thing here before I think we adjourn for the day. Even though this R matrix, let me find it here. Here we go. That variance covariance matrix of the residuals allows a different residual variance for each type of outcome, for actual and for ideal. It constrains it to be the same across gender. So in addition to looking at whether or not there's mean differences in each outcome by gender, I can also look at potential variance and covariance differences as well. So one more model to show you is how to do that. The extra part that allows the R matrix to differ between genders is this by thing in stata. This is model 1B, and the group equals in SAS. That allows every parameter in the R matrix to differ between the two genders. To be able to get a printout of what the R matrix would be for each, I have person 100 happens to be a man, person ID 103 happens to be a woman. I had to go into the data set and look at the index. So these numbers here refer to the order of the persons. So I sorted by gender and found the first man and the last woman, I think, to be able to find what numbers to put here. And here's what we get. So here's for men, and here's for women. Looks like they're pretty much the same. The correlation is pretty much the same. -2 log likelihood to compare their fit suggests that the difference is non-significant, so no adding 3 more parameters to allow the R matrix to differ between groups doesn't help the model. Now, by the way, this model in which everything gets to differ by gender, including the variances and covariances, not just the means, has a special name. Does this sound familiar? What if I told you that this was the same thing as a multiple groups structural equation model? Yeah, that is the framework in which group differences in things like means and variances are often entertained, but you can do it as a multivariate model in univariate software as well, with one catch. In this code, this by option here and this group option here just says, is the whole R matrix different between groups? It doesn't allow you to zero in and say, is just this variance different or just that variance different? You couldn't, there's no way to say, let these ones be the same and but make these ones different. You can't customize it. In structural equation modeling software, which we will learn shortly, you can customize it. So it's going to be more flexible in that regard. So, all right. I think that is an excellent place to stop. Questions on that? Homogeneous versus heterogeneous variance by group. No? Okay. Then let us call it a day. Let me know if you need anything. Otherwise, I will see you Thursday, okay? All right, hang tight, folks.